Before getting into testing the difference between means, we first need to cover independent and dependent samples. Two samples are independent when the first sample is not related to the second sample. For instance, let's say that sample 1 is daily time spent on social media by college males, and sample 2 is daily time spent on social media by college females. There is no possible pairing of members from these samples. Two samples are dependent when each member of one sample is related or corresponds to a member of the other sample. An example of this is the weight of individuals before going on a diet and the weight of those same individuals after 10 weeks of dieting. And dependent samples are often referred to as paired samples or matched samples. Now on to testing the difference between means. So let's say that we have two populations, population 1 and population 2. Maybe monthly household income in Texas and monthly household income in Vermont. And each of these populations has its own parameters, such as mu1 and mu2, the means, sigma squared 1 and sigma squared 2, the variances, and sigma 1 and sigma 2, the standard deviations. Many times we want to compare parameters from populations, such as the means for monthly household income in Texas versus Vermont, mu1 and mu2. But it is many times impossible or too costly to get all of the data from a population. So we can get samples from the populations, sample 1 and sample 2, and calculate their statistics, such as their means, x bar 1 and x bar 2, their standard deviations, S1 and S2, and their sample sizes, N1 and N2. We can then test a claim comparing the means of the two populations by using samples and comparing their means. In doing this, we always start by assuming there is no difference between the population means. So the mean for population 1, mu1, minus the mean for population 2, mu2, equals 0, or mu1 equals mu2. This is important. Remember, we always assume there's no difference between the population means. Keep in mind that when we perform hypothesis tests with two independent samples, we are testing a claim about the differences between mu1 and mu2, the population means, not the actual values of mu1 and mu2. For a two independent sample hypothesis, the null hypothesis, h sub 0, always contains a statement of equality, greater than or equal to, or less than or equal to. And the alternative hypothesis, h sub a, always contains a statement of inequality, greater than, not equal to, or less than. Just like in hypothesis testing with one sample, the usual pairing of hypotheses are listed here, with equals and does not equals paired, less than or equal to, and greater than paired, and greater than or equal to, and less than paired together. And you can look to the alternative hypothesis for the type of test. Does not equals is a two-tailed test. Greater than is a right-tailed test, and less than is a left-tailed test. Typically there are three different scenarios for hypothesis testing with two samples. The difference between means, independent samples, and population standard deviations, sigma 1 and sigma 2, are known. The difference between means, independent samples, and population standard deviations, sigma 1 and sigma 2, are unknown. And the difference between means for dependent samples. In the rest of this video, we're going to cover testing the difference between means, independent samples, and population standard deviations are known. And I'll cover the other two scenarios in future videos. To perform this hypothesis test, we're going to use a z-test, and there are four conditions that must be met. Both population standard deviations, sigma 1 and sigma 2, must be known. The samples must be random samples, the samples must be independent samples, and the populations must be normally distributed, or each sample size, N1 and N2, must be greater than or equal to 30. When these conditions are met, we use a similar process as hypothesis testing with one sample. Here are graphs for a left-tailed, a right-tailed, and a two-tailed test. And these shaded areas would be rejection regions, and these red lines are critical values. The shaded areas are the levels of significance, noted as alpha in one-tailed tests and 1/2 alpha for two-tailed tests. And the critical values are often noted as z0 for a one-tailed test and negative z0 and positive z0 for two-tailed tests. If a calculated standardized test statistic falls into a rejection region, it would mean to reject the null hypothesis. And a standardized test statistic that does not fall into a rejection region would mean to fail to reject the null hypothesis. The formula we use to calculate a standardized test statistic in a two-sample z-test is z equals the observed difference minus the hypothesized difference divided by the standard error. And mathematically, this formula is z equals x bar 1 minus x bar 2 minus mu 1 minus mu 2 divided by sigma x bar 1 minus x bar 2. In this formula, z is the standardized test statistic, X bar 1 is the mean for sample 1, X bar 2 is the mean for sample 2, mu 1 is the mean for population 1, mu 2 is the mean for population 2, and remember, we always assume mu 1 minus mu 2 equals 0, so this part of the formula will always equal 0. Sigma X bar 1 minus X bar 2 is the standard error. And the formula for the standard error is the square root of sigma 1 squared divided by n1 plus sigma squared 2 divided by n2, where sigma squared 1 is the variance, or the standard deviation squared for population 1. Sigma squared 2 is the variance, or the standard deviation squared for population 2, and n1 and n2 are the sample sizes for sample 1 and sample 2. So the formula completely written out looks like this. Alright, example time, and we'll go through step by step. A researcher claims there is a difference in the mean amount of money spent per month dining out of households in Iowa and Indiana. A random survey of 175 households in each state found a mean of $428 in Iowa and $441 in Indiana. Assume a standard deviation of 48 in Iowa and 59 in Indiana. Using a level of significance of alpha equals 0.05, do the results support the researcher's claim? I've listed and labeled all the variables on the screen that we're going to need. Step 1 is to make sure the 4 conditions are met. Both population standard deviations are known, both samples are random samples, as that was stated in the information given. The samples are independent, one sample from Iowa and one from Indiana, and the sample size of each is 175, which is greater than or equal to 30. So all the conditions are met. Step 2 is to write out the claim and identify the null and alternative hypotheses. The claim is that there is a difference between the population means from Iowa and Indiana. So mu 1 does not equal mu 2. And we know the alternative hypothesis contains a statement of inequality, so H sub A is mu 1 does not equal mu 2. The null hypothesis is the complement of the alternative hypothesis and contains a statement of equality, so H sub 0 is mu 1 is equal to mu 2. Step 3 is to identify the level of significance, which was given as alpha equals 0.05. Step 4 is to determine the test to use, left-tailed, right-tailed, or two-tailed. And because the alternative hypothesis contains the does not equals inequality, this will be a two-tailed test. Step 5 is to determine the critical value or values. And since this is a two-tailed test, there will be 2 critical values. Graphically, this looks like this, with our critical values, negative z0 and positive z0 here, and both of these shaded areas in the tails being rejection regions. Since the level of significance is alpha equals 0.05, and this is a two-tailed test, each of these rejection regions will be 1/2 of alpha, which is 0.025. And in the z-distribution table, that value is negative 1.96 and positive 1.96. So those are our critical values. Step 6 is to identify the rejection regions. And our rejection regions is any standardized test statistic value that falls in the shaded area, which is any value less than negative 1.96 or any value greater than positive 1.96. Step 7 is to use the formula to calculate the z-value, or the value of the standardized test statistic. And in our example, we have 428 minus 441 minus 0, as we always assume mu 1 minus mu 2 equals 0, over the square root of 48 squared over 175 plus 59 squared over 175. And this calculates out to z equals negative 2.261. Step 8 is to make a decision to reject or fail to reject the null hypothesis. On our graph, you can see that the standardized test statistic does fall in the rejection region to the left, as z, the standardized test statistic, is less than negative z0, the critical value. So in this case, we will reject the null hypothesis. Step 9 is to interpret the decision. There is enough evidence at the 5% level of significance to support the researcher's claim that there is a difference in the mean amount of money spent per month dining out of households in Iowa and Indiana. Alright my friends, that be the basics on hypothesis testing for the difference between means from independent samples when you know the population standard deviations. Hopefully this video helped you out. I do have more videos right there for you. Till next time, I am out of here.